All right, so what we are about to learn in this video lecture is a direct consequence after learning about the fundamental theorem of calculus, the second part. And so in that reason, usually this is taught and this is learned right after you have learned about the fundamental theorem of calculus, the second part. However, in the end, just think of this lecture here, think of this lesson that you're learning in this video lecture here as just one among the infinitely many applications out there of the definite integral. Okay, and so here we are at this lecture here with the title, the net change theorem. Okay, the net change theorem. All right, and so allow me to brief back a little bit at the fundamental theorem of calculus, especially the second part, because as I said earlier in this video lecture, this lesson we're about to learn here, this lecture we're about to learn through here is a direct consequence upon learning about the fundamental theorem of calculus, the second part. And so in that way, let's briefly look back at the fundamental theorem of calculus, the second part, to see what it says and then how that becomes how that gives rise to our net change theorem that we're about to learn here. Okay, so the fundamental theorem, the FTC, okay, the second part, part 2, stated the following here. So allow me to go a little bit skippy. Allow me to skip out the details in the wording. But the main idea of the fundamental theorem of calculus is about anytime you're taking the definite integral of a function f of x in respect to x and taking that definite integral from a to b, it's accumulation, and you have seen how I keep verbalizing the word accumulation to replace the idea of taking an integral. An integral is accumulation. Okay, so anytime we're accumulating on a function, okay, from a to b for here, then the fundamental theorem of calculus, part 2, stated that, and we've learned this result earlier, stated that all we do is just find the capital F in relative to this lowercase f right here, and evaluate that at b, and then that capital F evaluated at a. So as a reminder, capital F is that function where capital F prime of x equals f of x. Or in other words, the shocking result we've learned here in the fundamental theorem of calculus is that capital F relates with our main function in the integral problem here to be relates with that main function that here as the antiderivative. So fundamental theorem of calculus, the second part stated that all we have to do is first, big step, find the antiderivative of our function here, of our main function here, that lowercase f of x, and then evaluate the antiderivative at b and a, and then subtract out and take the difference. So here notice we have a difference. Okay, notice here we have a difference. Okay, and take the difference between the two values of the antiderivatives at two different integral limits right here. And that's what it is. And of course, so all of the worded details I skipped was so another details that was also important to this, but you won't see much impact until a much more advanced course. But the function we're integrating here must be continuous, okay, on the interval from a to b. Okay, but that's all about the details we need to get. And then any of the other extra stuff in the standard wording of the theorem, allow me to skip it out. Okay, so right here, as we are focusing on this part, primarily speaking, the relationship between this capital F and that F, where we're taking the integral, the definite integral on top of right here, is that capital F is the antiderivative. It's made clear, it's stated clear in this relationship right here. The point is capital F prime equals f of x. Okay, and so in that reason, and no, I just now I pointed out this where maybe I have not pointed out when we were specifically studying about the fundamental theorem of calculus, but what I have here is a difference. It's always a difference, and this time I would like to emphasize in that. Okay? And so now, in that reason right here, allow me to modify. Okay? So we know that when we take the definite integral of any function, then we're going to end up with the antiderivative, and then we're going to, according to the fundamental theorem of calculus, we are going to evaluate that antiderivative found there at the values, upper and lower limits of our integral. And so in that way, now allow me to erase these information, and let's stay focused right here in this function. But now I'm going to say in the net, the idea is as following. Okay, we, instead of working with with this fundamental theorem of calculus right here, we specifically indicate the version where it's starting out being some function f of x, and then we find the antiderivative. But now here, allow me to change this function. I'm going to change this function here, and I will come back and filling it out right there. Or how about let's take a look at it this way. If we're now taking the definite integral on the known derivative of a function, so here instead of f of x, I'm using f prime of x, lowercase f prime of x, okay, lowercase f prime of x, then, and as I just said earlier, this is the known derivative of some function f of x. We actually don't need to know what that function f of x is, but just say if we start out knowing the derivative, okay, of some function f of x, then now according to the fundamental theorem of calculus, the result here, the consequence here is that if we're taking the definite integral of this on this, because in the end a known derivative is also another function in terms of x, or in terms of that main variable. Okay, so now if we are taking the definite integral on a known derivative of a function in that setup right there in respect to x, then according to the fundamental theorem of calculus, we are going to end up with what? Hey, wait a minute, what is the antiderivative of this derivative? It has to be the function f itself. And now according to the fundamental theorem of calculus, we are going to take f, which is now known to be the antiderivative of f prime. It's that relationship, and we're going to substitute b, the upper limits of our integral, into the function, and we're going to substitute a, the lower limits of our integral problem here, into the function and subtract out. So, ladies and gentlemen, this is the idea about the net change theorem. Now, first of all, why is it called net change? This is a change. A difference is a change in function value. Okay? A change in the value of f of x, right, in the interval, okay, in the interval from a to b. All right, so it's a change. Okay, and I spoke earlier when we wrapped up with the idea of definite integral, is that a definite integral represents, and especially right after we finished, still in the same lecture at the end of the lecture where I talked about where I talked about the fundamental theorem of calculus, the second part, I indicated clearly that an integral, a definite integral, is represented as a net area. Okay, a net area. Okay, so now in this case here, we've extended that idea and we call it, this is now a net, it's a net change. Okay, the difference here is a change. Okay, and then it's a net change because sometimes the total change, the overall net change could be a zero right there. Okay, so that's once again the idea in force now, is that as a direct consequence from the fundamental theorem of calculus, is that, so now instead of taking the definite integral on any function, and then we arrive at the antiderivative, and then subtract the antiderivative values at two different limits, low limits and high limits, to get the answer. That's the original version of the fundamental theorem of calculus, the second part. But now we apply that to the relationship between the derivative. So what happens if we take the definite integral on a known derivative? Then according to the fundamental theorem of calculus, we will end up with the function itself. and the function itself, because the function itself is the antiderivative of that, of our starting out the derivative, known derivative here. And so now the difference between the two values here is regarded as the net change in the value of the function. Okay, in at least from the beginning to the end of that interval from A to B. Okay, and so now let's formulate all of that idea into a formal wording of what the net change theorem is all about. All right, so it's just simply now the wording is very simple. Well, we've learned from calculus 1 that the derivative is known as rate of change. It's rate of change in on behalf, relative to that original function. And so now I'm going to say the integral, okay, or the definite integral of a rate of change. Okay, this is what it is. The integral of a rate of change, okay, is the net change. Okay, is the net change, and that net change here is going to be this quantity. Okay, so textbooks do not put this in a box right there, but here I just want to emphasize your understanding. This difference here is a change in value, and it's we call a definite integral is a net change. Okay, so here it's just the net change of value. So anytime we take the integral of the rate of change right here, then we end up with the net change of the function, net change in value of the function between, in that interval from A to B. Okay, so it's not, it seems surprisingly easy to come up with this consequence. So at this point, since it's that easy, yeah, it comes right out from the fundamental theorem of calculus. So you probably don't see much impact of this, of realizing this. But here's the thing. Let me now point out a couple quick application or examples right here. It's not a formal problem, but let me point out when we actually apply our understanding of calculus into many fields out there outside of math. Okay, so think about if we're doing math in the business field here, okay, for business fields, then business field professionals work a lot, very intensively with cost function as a function of quantity. So this is cost, okay, or more precisely total cost, or revenue as a function of units. Right here, the number of units being sold. So I'm just pointing out an example. You don't have to be the master at this. If you're not, if you're learning this class but not dedicating your career path for a business, I will bring up other business. I will bring up other applications, brief applications after this. But so now in the business field here, the professionals in the business field, they work with these functions, cost functions or revenue function. Okay, and it will just cost function or revenue. So you will need to be in the field itself to know what these quantity means, or profits. Okay, but so if these are the functions represent the kind of quantities that business professionals work with, then rate of change in this, and again x here is the units, okay, being either being sold or being produced. Okay, it's the same idea right here, because at production level that we need to spend our cost, we spend our own money to produce X units, and that's why we have total cost function as a function. It's a quantity, and it changes depending on the quantity that we're producing, that we aim to produce. And then we're going to sell away at some given price right there. So I'm not trying to give a lecture on the business field or anything like that, but once we produce that many units right there, then we're trying to sell away at a certain determined price right there. So selling X units away come up with revenue, total revenue. Okay, this is total revenue. And then the profits here is what we actually earn in making, living right there. What we earn for making living. And so profits here comes out, after revenue subtract away cost right there. That's profits, how much we earn to enjoy our life and grow our business. Okay? And so that's revenue, that's profit, and that's cost, and that's profit. These are the quantities that, as I said, business professionals work with a lot of time and very intensively. And these functions are all in terms of X, variable being the number of units either being sold or being produced. Different way of interpreting it, but the same variable. Okay, but now that's just the function. And so when it comes to the rate of change, so C prime now means so now it takes more some deeper understanding of business fields. So here I'm just introducing right here, but rate of change, so C prime as at the easiest level, at the general level for anyone to understand. C prime relative to C, it's just the rate of change. Okay. So here, how about the rate of change level? Because any of these quantities in life, any of the quantities in life changes value. That's why it's fascinating to study about these functions, any of these functions. Okay, and now I'm specifically talking about the kind of functions that we see in business fields. And so C prime specifically for the professionals in the business field, they call that it's the marginal cost. But of course, in order to fully understand what that marginal cost does to your business, you have to take a course in business, a course or so. And then the equivalent version when it's total revenue, then rate of change makes sense generally is R prime right here. But that is for the business professional, it's called the marginal revenues. Okay? And then same way right here, instantaneous rate of change. For profits, then that so the instantaneous rate of change for profits, okay, we can call it like that way, the rate of change of profit. But here for the professionals in the business field, they call that the marginal profit. Okay, it's marginal profit. So that's just in the idea now is that if we're focusing specifically in the business field, then I'm going to pick one example. Let me erase this column right here. If we take the integral, okay, on the rate of change of cost function in respect to x, the number of units being sold, and take that integral, that definite integral from a given a x equals a to x equals b. So this is x equals a units, okay, produced, to x equals b units produced. And of course, we always stay in that agreement that b is higher than a like that. So what does this give? According to the net change theorem right here, then now anytime we're taking the definite integral on rate of change function. So here is just the general version, and over there on my other board we apply specifically to business field, and I will get to other fields later. But if we apply this definite integral on any of if we take the integral of a rate of change over a finite interval like this, then we will end up with the net change. So what is this net change in our business field right here? As a quick example I'm pointing out. So this is going to be, allow me to erase this. So according to the net change theorem, then integrating our rate of change for cost function here, we'll end up with the cost function, the total cost function at the production level, at the higher production level, minus the cost amount, the cost value at the production level at A. So this is, again, it's the change, but this is the net change. Okay, it's the net change in cost. And of course, for people who are working in business, then cost functions are most of the time positive. So instead of saying net change for the people in business field, they call it as a total change in cost. When you change, when your company, when your factory decide to change from producing A units to B units. Say you're starting out with your company trying to produce producing 10,000 iPhones or P phones or whatever, okay, and then after that you decide to change to 20,000. So there's a change from A to B, 10,000 at some beginning, and then we change to B units, 10,000 to 20,000, change in the units being produced right there. And that will cause a net change in cost. And that net change in cost can be a lot of times easily found by integrating. Take the definite integral on the rate of change. Okay? And I will get a little bit more in details in general about why it's better to go this way. Why not just subtract out the difference between the two functions if we have the function? But let me hold on to that explanation to later. The route we do in here is, once we had derivative, once we know rate of change, we can just easily take the definite integral on rate of change. So now it's not just business field, but it's sort of like a general setting right here. Anytime we know rate of change, we take the definite integral on rate of change. That will give us the net change in the total, in the actual function, the net change in value in the actual function. And here again, specifically for the business people, that's the total cost as we change production level from some A units to some higher number of units B right here. Okay, so that's a brief story about the business field, the brief story that the business field professionals are working with. Okay, so what about other fields? And I'm still working on this board of mine right here. For a reason, I want to leave the net change theorem there. So, science field. And there are a lot of fields out there that apply calculus, that apply our understanding of math like that. So, what about outside of a business field? We have chemistry, so here generally scientists use a lot of calculus. Okay. Scientists. So in science, now let me specifically look at a very well-known problem in chemistry. Okay, you see in chemistry, the chemists there, they work with chemical substances. Okay, chemical substances, and they measure. Let's say there's a chemical substance named C right here. And so C here is just the name of a chemical. It's not cost function. Cost function was a stop at the business field. Here I'm talking about the name of a chemical. So among the chemists right here, they use that symbol to represent the concentration of a chemical. Okay, the concentration of a chemical, and as a function of time. So the idea now is that as reaction on a chemical takes process. Okay, as a reaction progress right there, over time, one chemical is going to lose its own, because that's the way how a chemical reaction happens. One chemical is going to start losing its own to become a different chemical substance. That's what reaction in chemistry is for. Okay, that's what all of those reactions in chemistry are doing. Okay, so think about if we specifically pay attention to one chemical in a reaction right there, then in the beginning of the reaction, then we have a certain amount, and then as the reaction goes on, as the reaction progresses on right here, we're gonna lose that amount, and then it's gonna get turned into some kind of other chemical. So the idea now, see, there's a change in chemical concentration, and so by the way, we measure the amount of chemicals in terms of the concentration. And again, so it needs you, or it needs anyone learning from this lesson here to take some basic course in chemistry to understand exactly what I'm talking about right here. Okay, but I can only introduce in a brief level, and then I'll leave that there for your professional chemistry instructor or professors to explain more in depth about that. But so now we notice there's a change in the amount of chemical. Okay, and formally they call it as a concentration. And so if we notice the amount of change, so with that function right here as a function representing the amount, the concentration of a chemical at a time t right here, then, so t is time, okay, t is the time, because usually that's what the chemists do. And so the rate of change version, okay, so now that's a general study right here. So that's the amount right here. So rate of change, as far as rate of change, yes, for chemists, they study a lot about the derivative. So rate of change is the C prime. I mean, it's a little bit funny that we use a square brackets, included together with the function's name like that. That's one function, okay? But so C prime is the concentration. I mean, it's the rate of change, instantaneous rate of change of our concentration function. So this is concentration, okay, at time t, concentration of whatever that chemical C is, okay? And so it makes sense mathematically, or it makes sense according to calculus, understanding that C prime right here is the rate of change of that concentration, because as time goes on, we change the concentration amount, we lose away the concentration amount, like that. And so there's a rate how fast that losing or that gaining goes away, okay? So and I keep saying losing, but it doesn't always have to be losing. Because I'm saying losing because in chemistry right now, at this moment I'm thinking about the forward direction of a reaction, but but as some reaction, as some chemical is losing itself, some other chemical is going to start being produced at the end of the reaction. So some chemical will be produced and will come out. So the rate of change does not always have to be a losing. Some other chemical in a reaction can be gaining itself and keep being produced. Okay, so now the only relationship we need to know here is that there's amount and there's rate of change. There's function, there's the derivative. Okay, and so now again, there's that famous problem that you see now if we take the integral, the definite integral on our known, okay, let's say if we know the derivative of our concentration function, okay, so concentration function is here. If for any reason we know the derivative of our concentration, then we're going to simply take the definite integral from a time a to a time b right here, and that gives us the total change. Okay, that gives us now once again the concentration at time b minus the concentration at time a. And again, this is the net change. Okay, this is the net change. It measures the change, okay, in concentration of C, okay, in that interval from A to B relative to time. Like that. Okay, so that's what the chemists do. So I'm going to erase this. And still, among the science, all the different science that we're learning right here, physics, a very famous problem in physics right here. When we're moving, we're looking at S here is to be the position. Okay, so let's say a lowercase letter s be regarded among the word of the physicist. Okay, so lowercase s is a symbol for the position function, and t is time again. So at any time t right here, so the position of a moving particle, how's that? Okay, of a moving particle at time t. All right, so imagine as if I'm walking on a path. Okay, my position becomes different. I come to different position as time goes on because there's motion in me. And even if I'm not making any motion at all, standing at the same spot, I still have some position. I still have some output position. As time goes on, my position stays the same as time goes on. Okay, so in the end, generally for the physicist, this is a very common and a very famous problem among the physicists right here. We try to learn about the position of a moving particle at any time t right here. And so in that way, the rate of change version is S prime of t. S prime of t. is the rate of change, but now among the physicists, we famously know that as the velocity. So S prime of t, the instantaneous rate of change of our position, is going to be known as velocity. And I believe I also introduced this back in, for anyone who studied calculus 1 with me or differential calculus 1 with me. I also pointed out, the relationship between the S and S prime and velocity and all that when we learned about the derivatives and all that. Okay, but so now for any reason, when you're studying about the motion, of a moving particle, for any reason that you know the speed, or actually you know the velocity, okay? For any reason that you know the velocity, S prime of t, so formally that's S prime of t, you know the instantaneous rate of change of our position function, then simply taking the definite integral of that in respect to t over an interval from a to b right here, then that will give us, okay, so SB minus SA, because once again, just like what is stated in the fundamental theorem of calculus, and consequently we came to that net change theorem, this S right here is the antiderivative of the S prime. And so just like the fundamental theorem of calculus stated, we're looking at what? S, the antiderivative of S prime at B minus S, the antiderivative of S prime at A. We subtract out. And so again, what I'm seeing here, and this is a problem famously known among the physicists right there. This is called a net change. Okay, the net change in, hey, what was S again? S is position, so the net change in position. Okay, net change in position over the interval from A to B. Okay, net change in position in the interval from A to B. All right, and so that's some quick, applications of the net change theorem, in brief right here. So why is it that we're approaching net change? Why are we calculating net change this way? Why are we the point now? The question now is, the concern now is that why do we want, why not just, see, I in my explanation I explained that, there's a function, we know what that function is. There's a function that we understand, we're aware about what that is. And then there's an equivalent derivative version. There's a corresponding derivative version. Like say S is for position, there's an S prime being the rate of change, the instantaneous rate of change version, or among the physicists we call it as the velocity. For business people, cost, if cost is a function, is a quantity, then C prime is formally the marginal cost, but mathematically it's just the instantaneous rate of change. And then for the scientists right here, the concentration of a chemical is a quantity, is a function, and then we had the C prime right here. But then, so why not calculating? So this F right here, I'm generally writing in my net change theorem here can be, see, F can be that concentration function for the chemist. S here, F here can be that position function S for the physicist. F here can be the cost function for the business professional. Okay. But so in that way, back to the question I raised earlier, why not just simply doing the net change here by take the function value, take the cost value at the B production, and then minus the cost value, the total cost value at A production, and subtract out. If you are a chemist, why not just take the concentration of the whatever chemical that is at time B minus the concentration of the chemical whatever that is at time A right here, and subtract out. Okay, why not just doing that to get the net change? Okay, and then if you are a physicist, why not just find the position function, evaluate the position function at B and then subtract out the position function evaluated at A. But why not doing just that simple work? But here we actually go through the definite integral, take the definite integral of the instantaneous rate of change, of the rate of change. Why is that so? All right, so the problem here is because, as a matter of fact, when we actually apply a lot of these problems in real life application right there, out there, when we bring these understanding into real life applications. So I spoke about so now let me make a quick brief of some of those functions I discussed about within on this left board here. Okay, so as a brief summary of what I've mentioned. So cost, okay, as a function of units. So this is total cost for the business people. Okay, the corresponding rate of change version is C prime. Let me tell you, in reality, right there, a lot of time in the business field, it's easier for the business professional to measure and come up with function that models rate of change. So my word for that, rate of change a lot of times is easier to be found, to be modeled. So a lot of time we have rate of change function available immediately or derivative available immediately instead of having the actual function here. See, so that's why having cost function immediately is not as easy as knowing the rate of change of cost. Okay, so the same with chemistry here. The same with chemistry. I took chemistry myself right here, and I know it. When we studied the fascinating when it came to the study about reaction rates, I got very fascinated personally myself because surprisingly, we got laws. Okay, famous chemists in the past, the scientists in the past came up with these laws and rules that allows us to know the rate of change of concentration, and we can actually come up with the function for rate of change of the concentration of a chemical before we know the actual concentration. And so it's like I said. So now for the chemist people, okay, it's always easier. A lot of times, actually, I shouldn't say always, but a lot of times it's easier to know the rate of change in your concentration. When especially if this problem is about a reaction rate problem, okay, and so it's easier to know the rates, okay, rate of reaction, rate of how we lose an amount, or the rate of how we gain an amount of the concentration of a chemical. So it's always easier to start out knowing rates, and then from there we can take the definite integral to arrive at the net change in concentration. Okay, and so just like that among the physicists, and the problem that physicists do actually lives in every single moment of our life here. Do we drive? Oh yes, we do. Okay, do we walk? Oh yes, we do. Okay, do we walk at the same speed? Do we drive at the same speed? No, we drive at variable speed. Okay, or we walk at changing speed, and that's why it's easier. It's easier for us to notice there's a velocity, which is a function. It's easier to model the velocity function, the rate of change of positions, and then once we had that, then we're gonna come up with it's easier to come up with the position function by simply taking the antiderivative, and then we can from there take the net change by taking the definite integral on top of our rate of change. And that's the reason why the net change theorem here comes out as an important guarantee. It's an important guarantee that, hey, anytime we're doing this, if for any reason we start out by first knowing we had a known derivative, a known rate of change, then taking the definite integral on a rate of change. Supposedly, at your calculus level here, then rate of change most of the time is being referred as the instantaneous rate of change. I'm saying this in case I keep forgetting to say instantaneous rate of change. So if you start out knowing rate of change, taking the definite integral on rate of change will guarantee that you come up with net change in your actual function right here, where this function here came out being the antiderivative of that. Okay, and so after this general discussion, I am going to push that into a couple examples right there. I already had video examples for the business field professionals, for the business field students to explore how finding the definite integral on marginal cost, on marginal revenue, or on marginal profits will arrive to their net change in cost value, net change in revenue value by changing the selling amount from A to B right there. Okay, so I do have video lessons on those applications, and then look for my video applications, my video lectures on the application of with the moving particles or with the chemistry stuff. Okay. All right, and so it is unavoidable that we have to apply our understanding of calculus into solving quite a few number of physics problems in physics, and because it's just the way it is. Problems in physics were the beginning motivation for deriving calculus, for coming up with calculus. Well, at least that's what I believe from what I've learned and understand and understood. And so now, especially after we have learned, so this video, the lesson here allow me to introduce an application, an example where I apply the net change theorem. So it is highly recommended that this video lesson here is viewed after you have learned from my the general discussion of what the net change theorem is. Okay, and in this particular example here, in this particular lecture here, I am going to point out one example, and we only need one example, and you will get a generality of that. Okay, it is one example where I point out how the net change theorem can be applied in physics problems, especially for the problems wherein we are working with a moving particle. Okay, so now I am switching over to the wording description of our problem on the computer screen here. All right, so now with what we're having here, let's look at the description of the problem. We're looking at a particle is moving at velocity given by v of t equals t cubed minus 36t. So we have the function that models velocity right here. Okay, and then this function here at least is being modeled in this interval for t being from 5 to 9 seconds. And so yes, the description is indicating here t is in seconds and v of t is in meter per second. So the question is to find the displacement of the particle in meters, right, on the time interval from 5 to 9 right here. Okay, so this word of mine is highlighted and being printed in bold right here because I would like to mention a few things. So I want to leave this for your physics instructor to explain in detail. Okay, but as we're going through with this problem right now, I want to make a clarification, and then again, as I said, I want to leave all of that real good details for your professor in physics to explain right here. But in physics, so just like how I briefly introduced in the general discussion lecture with the net change theorem, then in physics a lot of time we use a lowercase s of t as a function for position. So s of t is position. Okay, as a position at position of a particle, of a moving particle. So a position at time t. So think about you driving a car. That car that's moving, that moving car of yours is a position. I mean, is a particle. And so at any time t right here, you reach to a different position right there. And the car can also stay stationary. Okay, so in the end, s here, lowercase s of t is a position generally. And so here's the thing. In the world of physicists, okay, velocity, as I have already briefly introduced, and I will introduce it here again, velocity is known as change or rate of change. Rate of change, okay, in position. Rate of change in position. Okay, it's rate of change in position, and yes, formally, physicists call that velocity. Okay, it's velocity. So it's a rate of change in position. But so now there's something unclear that I want to clarify right here, and again, your physics professors will really make it clear. Okay, but a lot of time in our daily language, rate of change in position is usually understood as how fast the car is moving, how fast we are walking, right? So usually we communicate with people using the term speed. Okay, so now when we are studying about math and calculus, especially you're driving your way into taking a course in physics right there, then velocity is not quite, okay, is not speed, It's more than just speed. Okay, velocity here, velocity is not simply speed. Velocity is speed with direction, because it matters that even you're only traveling on one straight path, you could be traveling forwards with a forward direction, and then you could be traveling backwards. Okay, and so anyone who studied calculus 1 with me, I also spent some time explaining about this. Velocity, notated in the physics problems here as a v of t function here, but v of t for sure is not speed. It's not quite speed. It's not exactly the same as speed right here. Okay, because speed is just simply how much distance over time that you travel. So you could be, but distance is just a physical distance. You could be travel backward and travel forward, like there are different directions. Okay, and so in that way right here, now I have to make it clear a little bit. So now, first of all, let me kind of put this aside a little bit. Now, rate of change, now velocity is the change, but change in position. In physics, there are two understandings. Change in position. The word displacement that you saw when I put that in the wording description of the problem earlier, the word displacement truly is, in physics, it means the change in position. All right. So before having a rate, before putting that change in position over time to get velocity, displacement is the change in position. Okay, displacement in the change in position. So think about it. In this particular problem where we're looking at the question, the displacement of the particle over the time interval from 5 to 9 seconds right here. Tentatively, the idea is the question is looking for, see, change in position. So the position at time t equals 9 minus the position at time t equals 5. Right there. That's what displacement is. Okay, that's what displacement is. And so, but now later on, and a lot of time in life, you will also hear the people call the term distance. These two terms are always being a little bit misused right here, or being misunderstood from each other. Okay, so now I have to get it clear with this, and again, I want to leave all of that details, clear details for your physics instructor to explain. But distance is not quite the change in position. Okay, distance is, say, think about it like this. I can, from where I start right here, okay, I walked forward and I walk back. Okay, so I walk back to the same spot. So as far as changing position, I might be ending up with 0 change in position, because I walked and I come back to the same spot. Okay, but then really, did I make 0 distance? Nope. So my displacement was 0. Okay, but did I make a 0 travel distance? Nope. I travel some physical positive amount of distance forward, and then I travel the exact same amount of distance backward to get back to my original position here. So displacement is quite different with distance right here. Distance here is the physical amount of distance to being traveled, that was travel. Okay, so this is so it has to be all positive. Okay, distance has to be positive, whereas displacement can be negative, can be even 0. Okay, so distance has to be strictly positive, and then distance here really is the sum, or just to make it easy to understand, how about the total distance that's traveled. All right, the total distance that's traveled. And so in that way, so why did I bring up velocity and speed, and all of a sudden, you know, I'm driving people's attention completely away to displacement and distance right there. So here's the thing. So just get clear with me that, so starting out with the function known as the position function, and rate of change of instantaneous rate of change of position function is known as a velocity, v of t. Okay, it's velocity. So here now I split into 2 columns. So here's the thing, ladies and gentlemen. integrating, see, to find the displacement, the change in position, then we can just directly integrating our velocity function, which is, and so yes, v is s prime of t, as I mentioned earlier, v is s prime of t. And so simply take the definite integral on that function directly on the function, on the velocity function from the interval from the a to b right here. And specifically in this problem that I brought up on the computer screen earlier and kind of took a break from there, this is going to be specifically just that problem. We can just do taking the definite integral from 5 to 9. That will arrive at the displacement change. So hey, how do I see this to be an application of the net change theorem? This displacement right here is the net change in position. Change in position, and it's a net change in position. That's what it is. Okay? But so now, speed, as I pointed out earlier, speed is quite different with velocity. So, but it's related. It's quite different, but it's related. Speed here is always the positive of velocity. So, mathematically speaking, speed is the absolute value of velocity. Okay? And so now to find distance, okay, then we're gonna take the definite integral of speed function defined as absolute value of velocity. It's not easy, but we will get to that as we get further to this. But just keep in mind right now is the velocity. Speed here is the absolute value of velocity, and then we're still gonna be taking the definite integral from over an interval given right there, and that's how we arrive at total distance travel. Okay, so two different kinds of problem right there. All right, and so now in this problem, in our problem, clearly speaking, the question in part A, we know that we have our speed here. We know that we have our velocity here, and t is measured in seconds and all that. Okay, and so now the question in part A is asking find the displacement. All right, so now clearly our goal here is to find out the net change in position, because our position function is as indicated in the problem. Our position function is s of t. Okay, and we're given the velocity function, but displacement is the net change in position between 5 and 9 right there. So in order to get this, now I'm going to move over to my other board, and the problem will come out easily. As we now realize the nature about the displacement, how the displacement is related to given velocity. So just like I said, the problem have for us starting out as a given velocity. We know velocity given. Okay, that's what the problem having for us at start, and that's why now finding displacement in this case right here. And specifically, it sets displacement in the interval. Okay, the net display. The total displacement on the interval from 5 to 9 right here. That is just simply this quantity, s of 9 minus s of 5. Okay, but now we realize that after learning about the net change theorem, this is a net change of position, and so now all we do is simply take the definite integral of our known velocity function. So in this case, we're looking at t cubed minus 36t dt. Okay, and integrating that and taking that definite integral from 5 to 9. Okay, and so now the math will come out easy from 5 to 9 right here. So the math now will come out. So that means our net change, our displacement, our total displacement for that, or mathematically is the net change between S9 and S5 right here. That is going to be, now our antiderivative is going to be 1/4 t to the 4th minus 18 t squared. Okay, and then we're going to evaluate that from 5 to 9. All right, so, and think about that, because we're skipping the constants here, but if we had the constant, if we have found a constant for whatever that is, then this function here, this antiderivative, is now the function for the position function. Okay, so it's being able to find the indefinite integral is also a convenient way Okay, to find, in case that you only need to find a general position function for other purpose of the problem. Okay, and so the skills that you learn here to be able to find an indefinite integral or definite integral is extremely vital in a lot of these real world application problems out there. So now I am going to evaluate and subtract. Okay, and so now I'm going to look at 1/4, 9 to the 4th minus 18 times 9 squared. Okay, and then I'm going to subtract, and here I have 1/4 times 5 to the 4th minus 18 times 5 squared. All right, and then give me a minute to quickly swing by my computer station right here to grab a final answer. All right, and so the final answer I have here came out to be 476. Okay, 476. So this is an actual applied problem here. So what should be the appropriate units for this problem? It's meters. Okay, it's all due to the fact that everything in this problem is measured, well, the velocity itself is being measured in meter per second. Okay, and so that means the position or change in position, we change our position by the 476 meters. Okay, and what kind of path that is, it should not matter. It could be just a straight path, a straight line path. Okay, but so now in that way, and I'm still going to retain this information here because that's general understanding of the, and especially for anyone studying about physics, it's always a misunderstanding between displacement and distance right here, and then the velocity versus speed. Okay, so velocity versus speed. And so in that way, let me leave this board here with two separate columns to distinguish the two right here. Let's look at part B of our example. Okay, so just like what I said, and just like in that reason I was pointing out earlier, now part B of the example, exact same given information over here. We're having a particle moving at a known velocity being t cubed minus 36t. So velocity is a function that of t. Okay, so velocity of that particle is changing depending on where, on what t instant that is. And then the time interval that we're looking at is from 5 to 9 seconds. Okay, and then the units being measured here is meter per second. So that's velocity. But now we want to find the distance. We want to find the distance traveled by the particle. Okay, we want to find the distance. And so I brought up that explanation. So now we're not finding displacements. Part A was finding displacement, and we simply took that integral. Okay, but now after we're done with part A, part B here is asking for finding the distance. And so now I point out right here, distance is found and okay, distance is found as the, okay, that's short for distance right here. Distance is found as the definite integral over the A to B right here. Okay, from A to B on that absolute value function. Okay, and so now as far as a setup for here, then allow me to move on to the other board and set it up. All right, so the distance traveled in that time interval is found by, so we put our t cubed minus 36t as velocity function in absolute value. Okay, and we're integrating that. Take the definite integral from 5 to 9 on that interval, on that over that interval in respect to t. But so now here's one general rule and pretty much the only rule how we find integral, or how, because eventually we have to find antiderivative. Okay, we have to find antiderivative, but we have never learned, and we will never be able to have a technique for handling directly the antiderivative of an absolute value. So we have to use a workaround. So take my word on this. anytime you're finding the antiderivative, or anytime you're working with a definite integral on an absolute value function, okay? The whole point of absolute value function is to force the function outputs at any time to be positive. We always want the function to be positive, okay? And so imagine things this way. This t cubed minus 36t could be positive in some part, it could be negative in some part. And so putting the whole function in the absolute value will make the portion, see, some portion of the t cubed minus 36t. I'm not saying that this is the exact graph for that, but at least putting that function in absolute value means the portion being below the x-axis here must be treated as the portion, must be treated as the opposite. That means being above the x-axis, like that. Okay? And so in that way, taking that philosophy in mind right there, we definitely have to see the graph a little bit. We have to see the graph, or at least do some math right here, because we need to find out where, see, if we have a graph right here, we need to find out where our function t cubed minus 36t will cross through the t-axis, the horizontal axis, to sink below. We got to find out which interval, that could be one or even more than one, which interval or which intervals making our function falling below, making our velocity. So this is velocity function. We have to find out where on the axis here that define the intervals where our function, velocity function, falls below the x-axis. And that involves setting v of t. That involves setting v of t to equal 0. That's what we do. Okay, so we have to start out by doing that. Okay, we have to start out by doing that. And so now doing that here, by starting out with setting v of t equals 0, we will lead to having t cubed minus 36t equals 0. Okay, t cubed minus 36t equals 0. And so this equation is simple enough to solve by factoring. We can factor out the t right here, and that leads to t squared minus 36 equals 0. And great, we can factor even further. We can factor further to get t, and then the t squared minus 36 here can be factored as t minus 6 times t plus 6. Okay, so now we're looking at a complete factorial form of our left-hand side right here. So solving this equation leads down for me 3 solutions. One of them is t equals 0. One of them is t equals negative 6 from that factor, and the other one is t equals 6. So there are three places on the t-axis here where our graph, supposedly, I'm not saying that this is the actual graph for t cubed minus 36t, our velocity function, but at least we found algebraically that there are three places, t equals 0, t equals negative 6, and t equals 6 on the horizontal axis where the graph crosses through. So, but now good news, we don't need to worry about that one. Why is that? Because our interval that we're working with is only from 5 to 9 right here. Okay? So in some other case where the problem gives us a larger interval, then you have to consider these points considerably. Okay? But here, as putting these points, considering these points with our interval given here, then I see that I don't need to worry about that one. Neither t equals negative 6, because these are both outside of the interval. So the only point where we cross the axis here is that it's at t equals 6. That's the only point where we cross the horizontal axis in between the interval from 5 to 9. Okay? But that's just to find the point where the graph crosses the axis right here. How can we determine? So basically, once we solve that, here's the situation. So anyone learning this with me, you are in the calculus level. So allow me to explain with those algebraic details so that later on you will know how to use that to carry on. And I'm trying to approach this without the graph so that you don't have to be too dependent on a graphing device like that. Okay, even though in these days you got the powerful decimals, you have the powerful calculator TI-83 or 84, which is quite standard in a classroom. You can also get the work done here by drawing the graph. But now the point is, So we know that the graph, so 5 is here, 9 is here, that's the interval. I mean, that's the interval, but the graph can cross at 6. So 6 is somewhere between 5 and 9. The graph can cross through, the graph for the velocity function can cross through that way, meaning left side, there's an interval is being positive, there's an interval being negative. Or the graph can cross the other way. 5 is here, 9 is here. Okay, 6 is between, the graph can cross like that. Okay, and I'm not exactly sure what exactly the graph for that is. But there are two different cases. So how do I know? But definitely we have to break our interval from 5 to 9, into two separate intervals. One interval from 5 to 6, and the other one is from 6 to 9. 5 to 6 and 6 to 9. Two separate intervals. But then what I'm about to show you is how to decide, algebraically, how to decide in each interval over here whether our velocity will be above or being below or not. Okay, all right, so now let's find out. Okay, so let's find out. You've learned about the idea of the sign chart back in your pre-calculus course, and we also used that pretty intensively in your days learning calculus 1. And so I'm going to use that sign chart again. 6, 5, 9. This is two separate intervals. Starting at 5, ending at 9, two intervals inside of that, broken up right here. So now I'm going to pick a value between 5 and 6, like a 5.5, for example. Okay, I'm going to substitute that into just my function. I'm substitute that into my velocity function. Now I'm talking about the velocity function, not the absolute value version. So the inside part right here is my velocity, not the absolute value, because I want to detect which interval between these two has negative velocity. Okay, so now I'm going to substitute like a 5.5 or 5.9, a value anywhere, generally a value between 5 and 6. We stay away from 5, we stay away from 6, we stay away from 9 right there. Okay, all right. Actually, I lied a little bit. Let me pull back a little bit. In this case right here, we do, it's okay to take 5 and 9 like that, but I didn't want to use those because, you know, we don't know anything beyond that, those 2 points of the interval. So I suggest getting values between, right there, and try to make it as close as what you've learned from your Calc 1 or your pre-calculus courses. Okay, and so now I take 5.5, substitute that into the function value. All right, so I quickly stepped out over to my computer station, and 5.5 into the v of t function gives me a negative, okay, let me highlight that in red ink right here. It's a negative sign, negative 31.625. Okay, so the actual value shouldn't matter too much, but the sign here matters right here. That means I know now that my velocity function is negative sign in this interval between 5 and 6. Okay, and then, well, I'm going to pick, let's say, 7. Okay, and substituting 7, because it's a value that can generally represent any value between 6 and 9 right here. Substituting that into our v of t function, the sign chart again. I found positive 91. Okay. This value 91 is not too important. What matters for me right now is the positive sign. Okay, so I now know that this v of t function, now right now I'm specifically focused to the function inside the absolute value, because we need to know whether the function is negative or positive in an interval, in a certain interval. So now I know that my function v is negative in the interval from 5 to 6. This is what I'm doing. Now I need to erase, or maybe let me just leave it there. So the real, here's a technique right here. The real interval on the absolute value of t cubed minus 36t right here. Keep in mind, it's all about, we want that function, even though there were some area of that function, some part of that function being below the x-axis. Even though so, I always want positive value. That's what the absolute value is for. But so sadly, the v function here is negative in the interval from 5 to 6. So I have to produce this integral as the following. One separate integral from 5 to 6. And in that interval here, I know that the function v of t is negative. And so now I'm going to turn that t cubed minus 36t. To ensure it's positive, I have to put a negative sign right there. Okay, and then in respect to t. So that's one separate integral, definite integral from 5 to 6. But purposely, so the good thing about this is now we can use the fundamental theorem of calculus because we took away the absolute value sign. We applied the correct treatment for that. So the rule now is that we have to apply negative signs. We put a negative sign in front of the function. Anytime in any interval that we know the function will be below the x-axis or negative. Okay, and then I'm going to need to accumulate. Okay, I'm going to accumulate. And so I'm running out of space a little bit. So how about, let me write it in smaller writing right here. So here from 5 to 6, I'm going to have a negative. Here t cubed minus 36t. Okay, that's one function. And then the other one here from 6 to 9 right here, same function, t cubed minus 36t with a dt. But this time there's no need to put the negative sign in front of our function because in this interval from 6 to 9, the function itself is already positive. So having absolute value or without absolute value, it's all going to be good. Okay, so now we really produce two separate integral problems. And then now just go ahead and find the two separate integral values and then add it in. Okay, now my board is getting tight here, and so allow me to just skip the step of fundamental theorem of calculus, but I'm going to just jump over to my computer station and grab the value right there. All right, so my calculation on the computer station gave me positive, so this must be giving me a positive answer now. So positive 30.25 here for that integral. And it gives me, so now I'm going to add with the other one here. It came out being positive 506.25. All right, and so now, so the work in the end, the work we're doing so far here is supposedly the distance, the total distance traveled in that interval from 5 to 9. And so now as a final answer, allow me to write it in this little amount right here. So distance is just now the total of, okay, the distance here is the total of the 30.25 and the 506, positive 506.25 added together. So now we're looking at 536.5, and the answer here is in meters. And that's how we handle a problem like this, where it's asking for distance. Okay, so anytime you are given a velocity, but you are asked to find distance, it's actually a little more tricky than finding displacement. You have to find the integral, you take the definite integral on your absolute value, on the absolute value of your velocity. And because of that, we have to carefully break it down into separate integrals, where each some of those here we have to apply the opposite treatment, apply the opposite sign here. If the velocity felt negative in that specific interval, and that's the whole idea. Okay,